Hey everyone, welcome back to this class on DC to DC converters. This week we're looking at reverse polarity protection, overcurrent protection, and voltage protection. So just as a reminder what we're doing, right? So we're basing these discussions on the DC to DC Book of Knowledge by Steve Roberts. And I've changed the schedule so that we'll be meeting on Mondays from 8 to 9 p.m. And the schedule is updated here on this link. All right. This is just a knowledge check from last week. So as a reminder, last week we took a look at electrical parameters, right? So the knowledge check is a little bit shorter than the previous ones just because we only had one topic. But you should go through these questions, make sure you can answer them, and you should be set for interview situations. So jumping right into it, we're looking at reverse polarity protection to start. And so reversing, Vn plus and Vn minus can be a great way to, really easy way to break things. Just for example, we've got electrolytic capacitors. So these are often used as bulk capacitors, right? They have a very large amount of capacitance, so they can store a lot of energy and hold up the input voltage. Um, but they have a interesting failure mode because they are polarized devices, and if you actually reverse the polarity on these pins, um, in that you connect Vn plus to this negative terminal and Vn minus to this positive terminal, in a sense forcing current to flow from this negative terminal to the positive terminal, well then it's actually going to just end up shorting out the capacitor. Right, and so this is going to obviously break your converter. Um, so it's something we want to protect against. Another example is MOSFET body diodes. So all MOSFETs have this intrinsic diode just due to the construction of the MOSFET and the silicon, right? So when a reverse polarity voltage appears across this MOSFET, it causes high currents to flow through this body diode, and it'll cause the MOSFET itself to actually break. So again, we need a way to prevent damage due to these reverse polarity conditions. There are these two main ways to add reverse polarity protection, and they often just require some kind of series element that prevents any kind of current from flowing when we've got reverse polarity at the input. So first off, we have the series diode here on the left, where it's going to be blocking current whenever polarity is reversed because of how diodes behave. Um, and then on the right here, we have a series MOSFET. In this case, this is a PFET, right? A P-channel MOSFET that's being used for reverse polarity protection. And so one thing to note is that MOSFETs need to be connected very specifically depending on what kind of MOSFET you're using, right? So there are P-channel MOSFETs and N-channel MOSFETs. You can't just connect them arbitrarily. You need to be careful with how you're using them. So again, here's the series diode reverse polarity protection circuit and how it operates. Here, when this battery voltage is applied properly, you can see that the diode is forward biased and allows current to flow to the load. Whereas if we reverse the polarity on this battery, this diode will be reverse biased and it'll actually not conduct current. So then current will be prevented from going through the load entirely. So this has the advantage of being easily controlled. Again, this is just exploiting the nature of how diodes work in general. But one disadvantage is that diodes do have a pretty significant forward voltage drop. And so at low voltages, this can become a huge problem, right? Especially if our battery voltage and our load voltage, if our load voltage is really needs most of the battery voltage in order to work properly, and the diode maybe has a 0.7 volt drop, well, then your load is not actually going to be properly powered there. So series MOSFETs can also work much like this series diode, but again, we need to be careful with how we connect it. So on the left here, we have a P-channel MOSFET, and on the right, we have an N-channel MOSFET. And so the way that this P-channel MOSFET works is that we need to apply a gate voltage, right? So this G terminal here needs to be less than the source voltage by at least some threshold V sub T. And so that's the threshold voltage of the um, oops, threshold voltage of this P-channel MOSFET. On the other hand, the N-channel MOSFET needs a gate voltage that's above the source voltage by at least some threshold. And so this is where we run into some amount of trouble with just adding in an N-channel MOSFET, right? Because in order to drive this gate and turn on the MOSFET, we actually need to raise the gate voltage pretty high up, right? It needs to somehow get above the source. So in order to do that, we can't just have some kind of signal that's derived from any of these other branches. We actually need to actively drive that gate voltage higher than the source there. So these N-channel MOSFETs are more efficient just due to the behavior or the physics of P-channel MOSFETs versus N-channel MOSFETs, which we won't get into here, but it's one thing to note. All right, so getting into overcurrent protection, these are the four main ways to protect against overcurrent. Right, so first we have the input fuse, we've got inrush current limiters, load switch, and output soft start. And we're going to talk about each of these here in these coming sections. All right, so fuses, first of all, these create an open circuit when an overcurrent event happens, and they will, most of them just break after once they create that open circuit and will need to be replaced. So obviously you want to pick a fuse that is rated for a current above your operating current, right? Because otherwise the fuse is just going to blow and then you're not going to be able to operate your circuit. And then there are two different types of fuses. There are slow blow fuses and fast blow fuses, right? So the main distinction here is how fast they create that open circuit. We usually want to pick out slow blow fuses because these can handle some overcurrent transients without breaking. And so we're going to talk a little bit about this, but there are inrush current events where the input current is actually a little bit higher than our normal operating current. So again, we usually want these slow blow fuses unless we have a really specific current threshold that we need to open the circuit very quickly, right? In which case we'd want to use a fast blow fuse. Another way to prevent these overcurrent events is to use inrush limiters. So this is a specific type of current that is used to slowly charge these input filter capacitors. So we always want some amount of capacitance to hold up the input voltage in case that the power distribution network has some kind of dips due to various load increases. But these capacitors, when we turn on our DC to DC converter, these are usually discharged at 0 volts. And capacitors will always have some amount of equivalent series resistance. And for these large bulk capacitors, especially like electrolytics that have a lot of capacitance, will also usually have a pretty low equivalent series resistance, which means that we'll have very high currents flowing through it, right? Because the current is inversely proportional to how much resistance there is. And so we actually need a way to, limit this inrush current due to all these capacitors. And so I say all of these capacitors because usually what's done is we have a bunch of these bulk capacitors in parallel, in addition to some other smaller filter capacitors, usually on the microhenry or nanohenry range, to filter out high frequency AC. But again, having all these capacitors hooked up in parallel only means that the equivalent resistance of all of these capacitors in parallel goes down, which means that we'll have even more current, right? We've got a bunch of these capacitors in parallel, so very high inrush current. And here is an example of an inrush current limiter that they use in the book there. The basic idea is that initially, right, this capacitor voltage is zero, so this transistor, right, this MOSFET will be turned off, the gate will be basically zero, and the capacitor will initially charge through R1 and through RL. So this current limiting resistor here, R sub L, is slowing down the current that's being used to charge this capacitor. And over time, the capacitor will charge up, and the voltage at the gate of this MOSFET will eventually reach the threshold value of this MOSFET, at which point this MOSFET will conduct, right? It'll be like a switch that's switched on, and it'll short out this current limiting resistor, right? Effectively getting rid of it in the circuit. It's just being shorted out there, so it's being ignored. And that's how this inrush current limiter works, basically. Another way that we can reduce these overcurrent events is by introducing a load switch. So obviously, when we have a load on the output, the DC to DC converter will naturally want to pull more current in order to drive the load. And one way we can prevent this inrush current is actually by waiting until the output voltage reaches a sufficiently high value before allowing current to flow through the load. And so this load switch circuit behaves very similarly to this inrush limiter that we actually looked at before here, right? So we're charging up the output capacitance, and at some point that will drive this MOSFET gate to allow it to conduct, and then that will in turn switch on the load, right? It'll allow current to flow through the load once we've reached a sufficiently high output voltage there. On a similar note, on the output side, we have output soft start, when this is used to slowly ramp up the output voltage. So this is a little bit more complicated, but right, this circuit here is very specific to this this chip, this RECOM R611 2P. And so the basic idea is that this adjustable pin here, VADJ, is initially pulled up to V out through this transistor via this, or sorry, yeah, pulled up to V out via this transistor here. And then over time, the transistor stops conducting, and so we effectively see an output voltage of that nominal output that is specified in this data sheet here. And so really this kind of is very specific to this device. I've implemented soft start in digital control, and it's a little bit easier because you're basically just incrementing a little variable, that represents the output voltage. But here, you really need to pay attention to how your circuit works and then how you can implement this soft start ramp. Typically, the reference voltage is hidden within the controller IC, but you do have a way of adjusting the feedback network to slowly ramp up the output voltage, I think. But it's something to consider, right? Okay, so that concludes overcurrent protections. Now we can talk about voltage protection. And so I make the distinction here with just voltage protection because we do need to protect against both overvoltage and undervoltage events, right? Not just in the case of current, we have to protect against overcurrent. There isn't really an undercurrent event. Okay, so here are the four main voltage events that we'll need to protect against, right? We have output overvoltage, input overvoltage, voltage dips and interruptions, and then input undervoltage, which is, related to these voltage dips and interruptions to some degree. So output overvoltage often occurs from really fast changes in current over time, right? This di by dt. So the load might suddenly decrease, due to, I wrote suddenly twice there, that's why. So the load might suddenly decrease, which causes the voltage to rise. Right, if you can imagine if it's the output is loaded down really heavily and all of a sudden it needs less current, then the voltage is just going to respond by going up to account for that less current. And we need a way to protect against that. Another way that these rapid di by dt's occurs due to the inrush currents that we talked about before. So these might charge up the output capacitance too quickly, causing the voltage, to increase very quickly. You might also have the case where feedback controller doesn't have sufficient margin and causes this overshoot. And that this is actually directly related to that first bullet point there, right? Our feedback controller actually responds to the load current changing. And so if we don't have good enough margin, then due to that step in the load, our output voltage will just go too high. And so the easiest way to protect against these output overvoltage events is to just use a Zener diode. So here you can see that they show this Zener diode that's just hooked up in parallel with the output voltage. And there on the plot on this right side here, you can see that the voltage, this output voltage is going to be clamped at the Zener, right? This Zener voltage here. It will, even though it tries to go above that Zener voltage, when we have this Zener diode, hooked up in parallel with the output voltage such that under normal operating conditions is actually reverse biased, it's going to have this characteristic where it just allows the output voltage to be clamped to its Zener voltage. So obviously you want to choose this Zener diode to have a Zener voltage that is above your nominal voltage. Otherwise, the output voltage will just always be clamped and your converter won't actually work the way you want it to. Similarly, if we look at the input side, so there are input over voltage events. We don't have too much control over these. We're actually being fed this input voltage from some kind of power distribution network or power supply. And so there can be electrostatic discharge, which causes very high and quick voltage transients. Another thing that we often look at are lightning strikes, but these are a little bit more complicated to protect against. But in any case, there are two main devices that are used to protect against these. First of all, we have metal oxide varistors. I actually haven't seen these in practice, but the book mentions them, and so and good, I'll talk about them here. But the main difference between these metal oxide varistors and these transient voltage suppressor diodes is that the MOVs protect against high current transients, whereas these TVS diodes protect against fast, really high voltage transients. So you kind of just need to understand what you're being, what your DC to DC converter is being fed in order to protect against it. I'm guessing some of the systems that I've designed just don't have these MOVs, probably because we don't need them, but you just want to kind of understand what your source looks like and design accordingly. So another thing to talk about is these voltage dips on the input side. So these are called brownout periods or blackout periods where the input voltage drops too low. And maybe it's just momentarily where that happens and maybe it comes back up. But we do need a way to, so oftentimes we need a way to hold up the output voltage even in these brief input voltage interruptions. And so one way that we do that is that we include capacitors with enough capacitance to store energy and hold up the output voltage while our input is browned out or blacked out. So here in the book, they have an equation where you can determine how much capacitance you need given how much backup time that you want and how much output power is being drawn from the converter, input voltage, and then minimum input voltage, and then the efficiency. And just using those parameters, you can determine, again, how much capacitance you need for this. They call it the bridging capacitor. And one thing to note is that in order to achieve this holdup with the capacitor, you will need a series diode because otherwise current will want to flow from our input terminals back into the source, right? When this source is browned out, maybe our input voltage is nominally 10 volts, but our source, for whatever reason, drops down to 5. Well, the capacitor will hold up the 10 volts for some amount of time. But since this is 5 volts here, current will want to flow from this capacitor node through, whatever circuitry you have between the source and the capacitor, and then back into the source. But if we have our diode here, this will block that reverse current, and which can discharge our capacitor there too fast. All right, and then last thing we want to talk about here is the input under voltage events, which also relate to overcurrents. So when we have low input voltage, this just means that more current is needed to achieve, the output voltage that we're designing for. And in order to protect against these high currents, DC to DC converters, these switching regulator ICs and the like will have an undervoltage lockout threshold. So this is usually implemented within the controller ICs, but if you wanted to add this functionality to your actual circuit, the book gives an example of how to do this just with a voltage divider network, tapping off the input voltage, right? And then generating error from some kind of reference voltage in order to switch on a transistor, which will then effectively load the DC to DC converter. And using this circuit, you can set these undervoltage lockout thresholds, right? So above this voltage here, the switch will be on, right? And then the DC to DC converter will start working. And then the switch will be off at this voltage below here. And here you can see what that looks like in this sort of this voltage diagram versus converter state, switch state there. Yeah, so that's all I wanted to talk about. Next week, we're going to look at filtering, specifically input filtering, output filtering, and these reflected ripple currents. So, yeah, thanks for tuning in.